So hello students, here is another sample problem video in beams, indeterminate beams by the matrix approach. So determine the nodal displacements and member forces. Also compute the support reactions. E is constant. So for portion AB, the moment of inertia is I. For portion BCD, we have 1.25 of I. But this is incorporated in the stiffness of each member by the formula which you already know. So first, for the fixed moment in AB, we divide the load into rectangular load and triangular load. The intensity of the triangular load here is 18, 36 minus 18. So for the rectangular load, WL square over 12, and it is counterclockwise at the left, clockwise at the right. So that's why it is treated negative, because in slope deflection equation, fixed moment is positive clockwise. So it is preceded with negative sign here. So W18 times 6 square over 12 plus W18 for the triangular load 6 square over 20. Check if it is 86.4. Again, 18 times 6 square over 12 plus 18 6 square over 20 is 86.4. On the other side, 18 times 6 square over 12 plus 18 times 6 square over 30, 75.6. Then for this upward force, summation moment about B equals 0, 91 point, FAB, so you just call it FAB. FAB times 6 plus 75.6, you write that equation, equals 86.4 plus moment of the load 18 times 6 times 3 plus moment of the triangular load 1/2 6 times 18 times 4. And I hope that you get 91.8 kilonewtons. Then for this reaction here, you just sum up forces Y. 1/2 of quantity 36 plus 18 times 6 minus 91.8, you'll get 70.2. Or another way is summation moment about A equals 0. Call this FBA. So FBA times 6 plus 86.4 equals 75.6 plus 18 times 6 times 3 plus 1/2 of 6 times 18 times 2. And I hope you'll get 70.2. I just explained it. Then for fixed moment BC, so we use integration here. So BC, negative integral, because it is expected clockwise, negative 18 dx, P is 8, differential P is 18 dx, A is x, then B is 8 minus x, this distance B, 8 minus x squared over 8 squared, limit 0 to 4. And that's the way of computing fixed moment in BC. And if you're not a student in structural analysis, definitely you cannot understand this. But if you're a student in structural analysis and you discuss slope deflection equations, then you know that it is negative 66 kilonewton meter due to this load. Due to this 90 kilonewton couple, the formula is MB, where B is distance from the couple to the right support, over L square, MB over L square quantity 2L minus 3B. So 2 times 8 minus 3B. And since the result here is positive, so it means it is clockwise. So clockwise as indicated here, 28.125. 66 is counterclockwise because it is negative. So for the other end, we just copy this integral. It is positive clockwise. So 18 dx times, interchange the quantity that is squared. So this time x is squared, and 8 minus x is raised to 1 over 8 squared. Remember the formula PA B squared over L squared, PA squared B over L squared. So that's the guide from slope deflection equations. Then for the moment, MA, fixed moment at the right end, MB, 90 times 6 over L squared, quantity 2L minus 3A, where A is the distance of the couple from the left support, which is 6. And the result is negative 16.875, so it is counterclockwise, as shown 16.875 clockwise. But this moment due to the load is clockwise, so that's why it is clockwise 30 here. Then finally, for portion CD, imagine that C is fixed, D is fixed. It is now this formula W15, 2 square over 12. 15 times 2 square over 12 is 5, which is this. So 5 counterclockwise here, 5 clockwise on the other side. Then the reaction WL over 2, because it is uniform and symmetric. So 15 times 2 over 2 is 15 kilonewtons, 15 kilonewtons. But we are interested of this load here. So therefore, at this node, which is node 4, 7, 8, the vertical load is 15 downward opposite to this, and the moment is counterclockwise positive 5 as shown here. So therefore, at node 2, which is B, the net moment is 75.6 plus 28.125 minus 66. So it is clockwise. The net fixed end moment is clockwise, but the nodal load is opposite to that clockwise, so counterclockwise. So again, 75.6 plus 28.125 minus 66. The result is positive 37.725 clockwise net fixed end moment, but the nodal load is opposite to that, so counterclockwise. And counterclockwise moment is positive universally or globally. Then at node 3, which is C, we have 30 minus 16.875 minus 5. So it is positive, so clockwise, but the nodal load is opposite to the clockwise, so counterclockwise. So 8.125. Again, 30 minus 5 minus 16.875 is positive 8.125 clockwise, the net fixed end moment, but the load is opposite to clockwise, so counterclockwise, and that's positive 8.125. Finally, at D, the load is 15 downward, and this is clockwise, so counterclockwise 5. That's positive. So we are only interested of the numbering for U4, theta B, U6, theta C, U7, delta D, U8, theta D. So 4, 6, 7, 8. But before that, these are the stiffnesses. For AB, we have EI. The I is just 1. So 12 times 1 over 6 cubed, that's 1 over 18. 6 times 1 over 6 squared, that's 1 over 6. Negative 1 over 18, negative of this, then copy 1 over 6. So for students in matrix structural analysis, you know that already. For those who are new, you have to enroll matrix structural analysis first, or study the global stiffness matrix of an element so that you can generate these values. So for BC, the moment of inertia is 1.25. So 12 times 1.25 divided by 8 cube, you will get 15 over 512. 6 times 1.25 divided by 8 square, 15 over 128. Then the negative of 15 over 512. Then copy 15 over 128. Then 15 over 128. 4 times 1.25 divided by 8 is 5/8. The negative of this, then half of 5/8, 5 over 16. The negative of the first row, then copy the second row, except that 5/8 and 5 over 16 will interchange position. So that's the technique. So I will not explain for CD anymore, and as well as the numbering. So we have F4, which is positive 37.725 because that's counterclockwise. F6, 8.125, positive also. F7, negative 15, downward, so negative 15. F8, moment 5, counterclockwise, so positive 5. And we have 4, 31 over 24, so you just add 4 here, and 4, 6, you 470, 480, so you can evaluate this. So as I said, students in matrix structural analysis know this already. So U4, U6, U7, U8 can now be computed as the product of the inverse of this matrix and this force matrix here. Your calculator is capable of doing that because there are 4 unknowns only, U4, U6, U7, U8. And U4, U6, U7, U8 corresponds respectively to theta B, theta B, theta C, delta D, and theta D. So these are the answers. 40.65688 over EI for theta B or U4. U6, negative 47.3284 over EI. U7, negative 118.657 over EI. U8, negative 63.3284 over EI. Then we can now compute the member forces for AB. So we copy the stiffness of AB, which is this. Then the displacements, delta A 0 because that's fixed. Theta A is 0 also. Delta B 0 and theta B 40.65688 over EI. Fixed forces 91.8, positive 86.4, positive 70.2, then negative 75.6. So since these are all zeros, the fourth column will be multiplied by this. So 16 times 40.65688 plus 91.8, you will get 98.576. Shear AB or reaction at A, upward reaction at A, 98.576 kilonewtons. Then moment AB is the moment at A, 1/3 of 40.65688 plus 86.4, that's 99.952 counterclockwise. And in lecture, it is negative because the positive sense at the left is clockwise. It is counterclockwise, so this is negative in the lecture part. Positive here because the sign convention universally is positive counterclockwise. Then negative 16 times 40.65688 shear BA plus 70.2 is 63.424 kilonewtons. Then moment BA is 2/3 of 40.65688 plus negative 75.6, so negative 48.495 kilonewton meter. Then for member forces BC, shear BC, moment BC, shear CB, and moment CB. This is the stiffness of member BC. We just copy it here. Then displacements, delta B 0, theta B, delta C 0, theta C, negative 47.3284. So fixed forces, FBC, which is calculated here. By the way, FBC summation moment about C0, FBC times 8 So FBC times 8 plus 90 plus 30, plus 90 plus 30, then minus 16.875, then plus 28.125, then equals 66 plus moment of 18 kilonewton load, 18 times 4 times 6, 18 times 4 times 6. So FBC is 45.844 kilonewtons. So that's why we have the friction force here, 45.844. Summation forces Y, you can compute FCB. So 18 times 4 minus 45.844 FBC, that would be FCB, 26.156. So 26.156. The friction force or friction moment at BC is, we have 66 minus 28.125, counterclockwise positive. Remember, 66 minus 28.125 is 37.875 positive. Then at the right end, this is 16.875 positive counterclockwise minus 30. 16.875 minus 30 is negative 13.125 or clockwise. So that's the friction force as friction moment CD. So therefore, shear BC is 15 over 128 times 40.65688 plus 15 over 128 times negative 47.3284 plus 45.844 is 45.062 shear BC. Moment BC, 5/8 times 40.65688 plus 5 over 16 times negative 47.3284 plus 37.875, you will get 48.495, which is equal to this numerically. Then shear CB is negative 15 over 128 times 40.65688 plus negative 15 over 128 times negative 47.3284, then plus 26.156, you will get 26.938 kilonewtons. Then moment CB, 5 over 16 times 40.65688 plus 5 over 8 times negative 47.3284 plus negative 13.125, you will get negative 30 kilonewton meter. Then for member force of CD on the next slide. So shear CD, moment CD, shear DC, moment DC, stiffness of member CD, then displacements delta C 0, theta C, delta D, and theta D. Then friction force 15, positive 15 left, positive 5 counterclockwise moment, positive 15, then negative 5. So shear CD is 15 over 8 times 0, of course, so we just obtain 15 over 8 times negative 47.3284 plus negative 15 over 8 times negative 118.657 plus 15 over 8 times negative 63.3284 plus 15, that would be 30. Moment CD, 5 halves times negative 47.3284 plus negative 15 over 8 times negative 118.657 plus 5 over 4 times negative 63.3284 plus 5, you will get 30. Shear DC, negative 15 over 8 times negative 47.3284 plus 15 over 8 times negative 118.657 plus negative 15 over 8 times negative 63.3284 plus 15, you will get 0. Of course, shear DC is 0. Then moment DC is also expected 0. 5 over 4 times negative 47.3284 plus negative 15 over 8 times negative 118.657 plus 5 halves times negative 63.3284 plus negative 5, so you'll get 0. For the reaction at A, it is just the shear in AB, and it was 98.576 kilonewtons. For the reaction at B, that shear in BA, which is 63.424, plus shear in BC, which is 45.062, and you will get 108.486 kilonewtons. For reaction at C, shear CB is 26.938 from the preceding slide, plus shear CD, which is 30, plus 30, 56.938 kilonewtons. So that's it for this sample problem on beams by matrix approach.